So now let's look at since we have learned about naive Bayes, now the assignment for naive Bayes will be very similar to the k-nearest neighbor with some modifications, right? So let's take two sets of features. The first set of feature, again, this is all on our donors choose data set, right? So if you look at this, we'll share these sheets with you. We'll share these IPython notebooks. So above this assignment, all of your feature engineering or your data matrix construction, all of that code is right here, right? So all of your analysis, everything is here, literally. So what is the data set? What are the features? How to load the data? All the pre-processing associated with it. We don't have univariate analysis here because we already learned it. It's not needed for, I'm sorry, it's not needed for building a naive Bayes model, right? Also, you have all the featureizations, your bag of words, TF, IDF, everything. And also, you also have how to prepare the data, right? So all of it is right here. So you can use the same sheet and fill up this sheet literally as a way to finish your assignment, right? Okay, so let's go step by step. The first set of features that we want you to work on is basically all the categorical, all the numerical features, and encode your project title as bag of words. Similarly, your project essay, we want you to encode it as bag of words. So this is basically all the categorical and numerical features, and the text features encoded as bag of words. That is set 1 of features. Set 2 of features here, if you notice, set 2 of features here are basically your same categorical numerical features, but your project title and project essay are encoded as TF-IDF vectors, right? So that's the key here. So we have two sets of features here, and we want you to train a multinomial naive Bayes, right? The reason, so there are two types of naive Bayes, right? There is your binary naive Bayes, where you have your binary type of naive Bayes, also called as Bernoulli naive Bayes, where for every categorical variable you have either 1 or 0. Imagine if you have categorical variables which are binary or which are from Bernoulli distribution. Bernoulli basically means just like coin tosses. It's either 1 or 0. It's heads or tails, right? So when we have something like that, we use something called as a Bernoulli naive Bayes. So if you go to scikit-learn, okay, you have the Bernoulli naive Bayes here, and it clearly says that naive Bayes classifier for multivariate Bernoulli models, right? Clearly says, and it's designed for binary or Boolean features. Your function reference in sklearn tells you what it does, okay? But if you think about it carefully, what we have here in bag of words are basically counts. They are not binary, they're actually counts. The count of number of times a word occurs in title here, number of times a word occurs in essay. Similarly, TF-IDFs are fractions, right? So when you have counts, we use something known as multinomial. We use something known as multinomial naive Bayes. We use something called as multinomial naive Bayes. And that's what we want you to use. There's something called as multinomial naive Bayes that we want you to use. So to understand multinomial naive Bayes, you can just Google search sklearn multinomial naive Bayes. Okay, of course, it's basically naive Bayes classifier, and here it says that it works for discrete features or categorical features or discrete features like word counts. This is nothing but your bag of words, right? Or it also says it can also work for fractional counts like TF-IDF, right? So we want you to use these multinomial naive Bayes instead of the Bernoulli naive Bayes because it can easily handle your bag of words and also TF-IDF as given in the description here. Right? The mathematics, everything stays the same. Small changes, that's it. Instead of a binary variable, you have count or fractions here. Right? Okay, that's good. So please do this assignment not using Bernoulli naive Bayes, but using multinomial naive Bayes. That's very important. So as part of this assignment, just like the way we want all of our assignments to be thorough, we have seen this in k-nearest neighbor assignment, right? We do all of our assignments very, very thoroughly. So we have seen hyperparameter tuning in k-nearest neighbor where we try to tune the best k. Here the hyperparameters are alpha, right? Your Laplace smoothing or your Laplace smoothing or additive smoothing type of variable here. So if you see multinomial naive Bayes, there is a hyperparameter alpha here. The default value is 1.0. So we want you to tune that hyperparameter, right? So on both these sets, so you have two sets of features. Please find the best hyperparameter value, which is the best value of alpha, which maximizes the AUC. The metric, the performance metric here is AUC. We want you to find the best alpha value in both these instances. For both these instances, we want you to find the best hyperparameter or the best alpha. To do that, just like in k-nearest neighbor, you can use k-fold cross-validation or simple cross-validation. Just like again, this part is very similar to your k-nearest neighbor assignment that we already done, right? Here, just that the hyperparameter is changing. Rest everything stays the same. You can use grid search or random search or write your own loops. That's perfectly okay, right? So here, what we are changing here is we are changing the features. Actually, we have used the bag of words features even in k-nearest neighbor. We are literally changing the model only. Literally, that's what we are doing, right? And the representation of results, we have already seen these plots, right? I've already explained these plots in the k-nearest neighbor assignment, right? This is basically as your hyperparameter changes, how does the area under the curve change for your trained data and validation data, right? So this anyway you have to do to find the best hyperparameter, number one. And once you find the best hyperparameters, train the model using that hyperparameter and plot the AUC for both your training data and test data. This is exactly the same. See, whatever code you have written in your k-nearest neighbor, you can reuse it for many of these tasks, right? Also, we want to see the confusion matrix. Again, whatever code you have written for k-nearest neighbor. So we have explained these plots. We have explained these two plots. We've also explained the confusion matrix in lots of details when we discussed about the k-nearest neighbor assignment. It's on the same data, slightly different featureizations, but everything mostly stays the same. Now, as far as feature importance is concerned, there is a small change, right? In the feature importance section, we want you to find the top 20 features from feature set 1 or feature set 2. You can pick any one of them, but just clearly state whether you're doing it for feature set 1 or feature set 2. Okay. And you can find the top features by using this coefficient parameter, by using the absolute value of the coefficient parameter in the multinomial naive Bayes. So we have also given the link here. So for example, if you go to multinomial naive Bayes, right, once you train your whole model, it gives you these coefficients. It gives you these coefficients, which is used in interpreting the multinomial naive Bayes. So please take these coefficient values. You'll get one coefficient for every feature you have, and pick the top 20 features that you have, right, based on the largest absolute value of the coefficient parameters, right? So this is very simple. All of this is available for you in this documentation. Play with it, work out the solution. It's not very hard, by the way. It's just literally a function call. And we want you to print the corresponding feature names. We want to see what are the top 20 features, either in feature set 1 or in feature set 2. Pick any one of them, but please clearly state which one you're picking. And when you're picking it, please print the top 20 features using the coefficient parameter. You don't have to write any extra code. These coefficient parameters are readily available once you train a multinomial naive Bayes. And just like in the case of, so this thing has changed from k-nearest neighbor, right? This thing has changed, right? The other important thing is we want you to summarize all of your results here. Okay, when you have used, so for set 1 and for set 2, what all hyperparameters have you tried, and what is the AUC that you obtain and things like that, right? Very, very simple, nothing fancy. This is a very, very simple extension to k-nearest neighbor. So if you have done your k-nearest neighbor assignment, which we strongly recommend you do before you come to this assignment, because you can reuse a lot of code. You can reuse a lot of code that you have written for the k-nearest neighbor out here. Okay, there will be some changes, obviously. There will be some changes. But if you've done your k-nearest neighbor assignment properly, this whole assignment, you can literally finish it in 1 to 2 hours. It's that simple, trust me. Because you are just changing the model slightly. Everything else falls in place. You can just reuse the same code that you've written for k-nearest neighbor. Just change the model slightly, because you already have these bag of word representations that you worked out in k-nearest neighbor. So once you do your first assignment, these assignments will become extremely easy and extremely fast for you.